is a new video where I will talk about optimal control for linear systems. To understand the problem, let us consider that we have this exercise. We want to minimize a quadratic cost subject to constraints on the dynamics of the system and the states of the system, and the inputs that we apply must be in some constraint region, and we have some conditions on the terminal state. For example, here we want to arrive to 0. In this exercise, we will take a very simple case. We will consider that we have a second order system of this form, ax plus bu. We have this system, we have this one input. The constraint set that we will consider that we have to bound our state x1 and x2 because we have two dimensions in this specific example. So they have to be constrained bit less than 1, and also we will allow to apply maximum 1 unit of input. So here it will be between -1 and 1. We will simplify just because we want to just explain the idea. So we will take into account the weighting matrices, this Q matrix 0, 5, 0, 5, and the weight on the quadratic term on U is 1. Okay, we can later play on these matrices to see their usefulness in the control and how to obtain a constrained optimal control. So the problem number 1 that we want to solve. So in order to solve the above optimal problem, we have to make a suitable discretization. To this end, we will choose that we have a sampling time delta, which is the final time, so the horizon capital T, over the number of samples big N. Okay, so N is the sampling intervals over the prediction horizon T. So during this sampling interval, we will have to find an open loop input that is piecewise constant, so as if we are using zero order hold and discretized digital systems. So we will, between two samples or during the sampling time, the input is kept constant, where k goes from 0 to n minus 1. So we want to discretize this problem. So before going into the details on how to solve this problem specifically, let us go a little bit about the theory about controlling this system. And we will go to another book here. So we go to chapter 8 of this book, and we let us a little bit understand the problem. So it is called a linear quadratic optimal control. So we have this system, linear and time invariant, x t plus 1 equal ax plus bu, and we want to find the input such that we minimize a quadratic cost of this form over a finite horizon of n steps. So we have xk is the state vector at time k, obtained by starting from the state x0, the initial state, and applying the system model. So the dynamics of the system A and B will give me xk plus 1. So if I know xk and u at time instant k, I will find xk plus 1. This is the linear system. Let us return a little bit to this cost function. So it is composed of 3 terms. The first term concerning the terminal cost, so the cost at xn, so after n steps. And here we have a quadratic term, the first one related to xk, so we have the addition from 0 to n minus 1. And also we have a quadratic term related to the input u. We have this finite time optimal problem. Now let us forget that we have constraints on the input and on the state as cited in the exercise. So here we have to find the input u that minimizes this cost quadratic cost function subject to the constraints on the initial state and also on the dynamics of the linear system that we are studying, and k is from 0 to n minus 1. This problem can be solved uh, either by batch approach or iterative approach. So let us see first of all the first approach, the batch approach. So the equality constraints that we find in the previous equation, these equality constraints, can be written in explicitly using the future states, so x1, x2 until xn, and also as a function of the future inputs u0, u1, and so on. So to understand, let us see the first line. So x0, so the initial state, equal x0, I here is the identity, plus 0 times u. So x0 equal x0. Now let us go one step further. So x1, what is x1? If we look again here using this equation, so x1 equal a x0 plus b u0. So here we have x1 is equal to a x0 plus b u0, and all the terms here are 0 here. So again, now if I want to find x2 in function of x1, it is x2 equal ax1 plus b u1, but replacing everything, we will have that at the end xn is equal to a to the power n times the initial state, and these terms relating a and b with the input vector from u0 to un minus 1. So the vector that we will apply during control horizon, for example. So here, as we see, all the future states are explicit functions of the present state, so the initial state here, and the future inputs that we will apply, so u0, u1, and u2. We can change a little bit the notation. We can call this big X. We can call this as upper script X, and so on. So we can write it in a compact form in like this. As you see, we have this vector or matrix depends on A. This matrix depends on A and B. And this is the initial condition or the present state. And this is the input vector that we want to find. Okay, if we do the same thing to find the objective function, so it can be written using the same thing. We can write that the cost function that we get here, we can write it in a compact form using the big X that we are using here. So we can find that Q bar is the concatenation or the block diagonal of Q's and P, because here we have the terminal state, and also for U we can block diagonal all the R's, and as we see that these are semi-positive matrices. So replacing these equations together, we can find that the cost function is a positive definite quadratic function of u0. Look here, this is the initial candidate of u, this is h, which depends on s upper script u and these terms, this is f, and this is y. As you see here, this is a general formulation for the cost function using the batch approach, and as we see, we can find u0 and these matrices. So here we don't have any constraints, so we can also find the minimum by calculating the gradient equal to 0 and setting it to 0, and then we can find the explicit expression of u using all these matrices. It is not the objective of this video, but just to introduce. We can also use a recursive approach. So here we will use dynamic programming, so to solve the problem in recursive manner, starting from the end state or the end solution, going back to the initial solution or initial cost function. So we we'll use the principle of optimality. You can refer to one of the videos that I made on dynamic programming to understand the idea. In simple words, we know that one step cost to go can be obtained by this expression. So we are going at the end of the optimization, and we will see that we can also find the solution for this one step cost to go. And if we do the same thing but now with two steps, we will see that we will arrive also to a similar form of the previous expressions here. So we can find this expression of n minus 2 forward solution or two-step problem, and we can make this in an iterative way until we find the solution of the problem. This you will see in other courses on optimal control. It is called discrete-time Riccati equation or Riccati difference equation. We want to find an optimal control, constraint optimal control of this system with these constraints on the state and with this quadratic cost to solve or to minimize using these Q and R, these weighting matrices. So the idea is how to use quadproc for this problem. So let us turn a little bit to the theory now. We go to chapter 11 of this book, and it talks about constraint optimal control. So again, we have the system. Now the state is constrained and U also is bounded. So we can consider that we have this polyhedra that contains the feasible solutions of state and on the input. So remember, the cost function is a terminal cost term and some terms. We can find different formulation using different norms, one norm, infinite norm, or squared Euclidean norm. We will take this for this problem because this is what we want. So the cost function is a terminal term here and the terms that we see here, and this is called constraint finite time optimal control problem. We want to find the control U such that it minimizes this cost function or this cost function subject to the dynamics of the system from k0 to n minus 1, and also that the state, the actual state, the present state, and the final state, the present state is feasible, the input that we apply is feasible, and the terminal state belongs to the final state. So n is the time horizon, xf is the terminal polyhedral region that we want to arrive to, u0 is the optimization vector that we want to find or to use to solve this problem, and also we consider that the initial state is inside the feasible state. This is very important to find the solution or for this optimal control problem. There exists a control sequence or a control vector such that the present state is feasible, this vector is also feasible, the final state is in the final desired region or polyhedra, and the dynamics of the system is verifying this equation. So the patch approach, so there exists a control vector such that the present state is feasible, the input is feasible, and we have this dynamics and the terminal cost. The definition of this set requires many things. First of all, that any initial state, there exists a feasible sequence of inputs. And this feasible sequence of inputs will keep the state evolution in the feasible set big X at future time instance. And it will forces the final state to arrive to the final destination at time equal n. If we want to rewrite the input and state constraints in this form, so we know that AX less or equal BX, and the final state verifies this expression, and the inputs on U verifies these constraints. We can write everything in a compact form. So we have this important expression. So this big GI is multiplied by u, this big EI multiplied by the state, and all of this less than or equal this big vector or matrix WI. Let us see line by line. So the first line here means that the first element of u is less than BU, and so on, as you see here on the diagonal. Then here at this line, we will start putting the constraints on x. So ax is less than or equal bx. Here we have negative because here we have minus. We will continue by replacing ax and as we see before, and ax2 and so on. And here at the end, we multiply by AF because we have also constraints on the final state, so we'll have this final expression. So return to the initial problem. We want to find the input U0 that minimizes this function with these constraints on the state and on the input and the terminal state. A given U0 is feasible for this problem if and only if at all time the state that we obtain by applying these control sequences and with this system model are feasible in Xi. This is just to remind you that how to find feasible solution for this problem. So we have to respect these conditions. I will not talk a lot on these theorems. You can see them later, or you can try to prove them yourself. It is just to confirm you that we will find a feasible solution. We have this problem that we want to solve in general way. We can write this problem as we have seen before using quadratic programming and using these things. We will find that we want to minimize this thing. So here we find quadratic, affine, and the final state. We can write everything in function of the initial state and the initial candidate, and this matrices F and H and Y as we seen before, subject to this constraints that we seen also in this equation. This is what we have seen, okay? And I will click here to remind you of what are the expressions of H, F, and Y. H, F, and Y. This is H, this is F, and this is Y. And H, as you see, depends on this big S, Q, and R bar. And here F depends on this S, Q bar, and S. And here depends on SX and Q bar and so on. And these Q bar, if you remember, they are the block diagonal, and here the block diagonal of R. By any solver that solves quadratic programming or QP. So here, if you want, the detailed expressions of Q, of G0, E0, and also the written state and input constraints here, you will see that we have zeros here, AX, zeros here, BX, BF, BU, zeros here, AUs, and here A and I, and so on. And the constructed cost function depends on the diagonal block diagonal of Q and P and R. So here the solution, we are using quadproc, so we have to put some options on the settings of the optimization. So here we are using, for example, interior point convex, but we can use another thing. Here we want to make an MPC, as I told you. So first of all, we find to solve the problem, the quadratic program problem, and then apply the receding horizons that we will see later. So here we have prediction time, delta, so we have n steps, so it is big capital T over delta. Here the system that we want to solve, we can discretize it using zero order hold, using C to D, so we'll get the discrete time system. The terminal state here in this case is 0. We will write, for example, Q equal 0.5 and R equal 1 or 10. we can play on these things. Here are the initial conditions, and here are the initial guess for u0 and x0. We know that the state must be between -1 and 1, so here we have two states, and u between -1 and 1, so we have these matrices. Now we want to write the problem under the form of quadratic programming, so we have to find f, h, and a, and so on. So what is h is the quadratic part of the cost. Here we don't have linear cost, so linear part of the cost, the inequality constraints, the equality constraints, the initial guess. So x0, remember here it is not the state, it is the vector of the initial vector of the input that we want to apply to solve the problem, and we add the options for the solver that we explained here. We start writing the problem. So we write the inequality constraints, we write the block the diagonal of AX, and at the end we will find that we find the state constraints for the terminal state here, the equality constraints. So we prepare the equality constraints by zeros, and then we try to complete them as what we shown theoretically. So here we complete with zeros and a and I and so on. So if we return here, you will see these i's and these a's. For the equality constraints, on the initial constraint and the terminal constraints, go and see these conditions. So we have ax, bx, and au, bu. So we'll see it here. So we have this terminal and so on. We will concatenate the q and r, so to have this cost, final cost. So this h is q and r as we have seen here, so q and r. We, for example, we can write that to print just to see the iterations. So from 1 to MPC iterations that is given, we can choose it here. For example, we will find 50 iterations, so 50 times 0 delta, so it is for 5 seconds. We will solve the problem using quadproc, putting h and f and everything here. This will give me the open loop predicted optimal state and input sequence. We will store it because we want to make the closed loop. We will measure, so we will apply the first input, the first sequence to have the second measurement, so to close the loop. Then here we can also make use the previous solution that we found just to accelerate, which is called warm start solution for the next time step. And here what we will get in the figures. So here just to show the figures that we find. So here the iteration that we get for each k until 50. Here we go all the trajectories that we will have, and here is all the sequences in open loop that we find, and here the closed loop input that we apply to stabilize the system. So as you see, it is between 0 and -1. I hope that you appreciate this video and try yourself to code this yourself and try to change the system to or the constraints to find or test different cost parameters to study their effect on your system, which is do not forget it is a linear system. Thank you for watching this video and hope to see you